Hi everybody, today we want to show how to transform a matrix into its reduced row echelon form using Gauss-Jordan elimination. In the previous video, you will find the link in the description below, we showed how to transform this matrix that you now see on the screen into a row echelon matrix with the usual three operations on the rows of a matrix that we will recall very soon again. Notice that this matrix on the right is not reduced because above each element 1, we would like to have a bunch of zeros, but instead we have -1, 6, and -2. It is, however, row echelon, even if it is not reduced, because we have our stair step, where each corner is equal to 1, and below the stair step, all the elements are equal to 0. If you don't remember the difference between row echelon and reduced row echelon, then you may need to take a look at other previous videos of mine where I explain these differences. Of course, you will find the links in the description below. With Gauss-Jordan elimination, we want to go even further. So far, we worked below the stair step. Now, we want to work above. The goal is to find a reduced row echelon matrix starting from the one to the left. At the end of the process, we will obtain this matrix on the right, where we have a stair step with all the corners equal to 1, but we also have all the desired zeros above each corner. But how do we get to this point? Very quickly, you can skip this part if you already watched my previous videos. We are only allowed to use the following three operations. We can interchange two rows, we can multiply a row by a scalar different from 0, and we can sum up one row with a multiple of another row. Here, all the three together. We can finally start our transformation. As for the first step, we would like to transform this -2 into a 0. So what we do is to sum up the second row and 2 times the third row in order to cancel the value -2. Let's proceed element by element. We first have 0 plus 2 times 0, which is equal to 0. 1 plus 2 times 0, which is equal to 1. -2 plus 2 times 1, which is equal to 0, as we wanted. 2 plus 2 times 0, which is equal to 2. And here, the final solution. As for the second step, first of all, we start with the last matrix that we obtained in the previous step. Then we notice that we would like to eliminate this element 6, which we would like to transform into the number 0. In order to obtain this, we work with rows 1 and 3, and in particular, we do row 1 minus 6 times row 3, so that the number 6 will become 0. Let's do it step by step like before. 1 minus 6 times 0 is equal to 1. -1 minus 6 times 0 is equal to -1. That we work on the number 6 that we wanted to cancel. And actually, we obtain 6 minus 6 times 1, which is equal to 0. And finally, -1 minus 6 times 0, which is equal to -1. And here we have our final matrix. Now you can see that above this, we already have a bunch of zeros. And no other number is allowed, so that's it for this column. It only remains to work on this number -1, which we want to transform into 0 as well. That's the object of the next step. Again, we start from the last matrix that we obtained in the previous step. And we now do row 1 plus row 3. That gives 1 plus 0 is equal to 1. -1 plus 1 is equal to 0. 0 plus 0 is equal to 0. -1 plus 2 is equal to 1. And this is the last step that we had to do. In conclusion, here we are with the reduced row echelon matrix that we wanted. Unlike Gaussian elimination, with Gauss-Jordan elimination, we obtain a unique matrix. There are no other reduced row echelon matrices that can be obtained from the initial matrix. And this is actually the most important difference between the two methods. And that's it for today. Thank you very much for watching. Please don't forget to like, comment, and subscribe. Thank you very much again. Bye.